Hello and welcome, dear students. Today we are going to discuss the topic relief features of a watershed and their influence on hydrology. Before we begin, let me ask you something very basic. Have you ever wondered why some rivers flood very quickly after rainfall while others respond slowly, or why some valleys are deep and rugged while others are wide and gentle? Much of this difference comes from the relief of the watershed, the shape, slope, and height of the land. Relief not only directs the movement of water but also influences erosion, soil formation, sediment transport, and vegetation growth. Understanding relief, what is it, and how relief controls these processes helps us predict floods, manage watersheds sustainably, and appreciate the dynamic interaction between landforms and water. Let us start with relief. Relief is the difference in elevation within a given area, watershed, or landscape. It reflects how high or low a land surface is and the difference between the lowest and the highest points in that land surface. Now the question is how relief is formed. We know the crust of the earth is dynamic. It has moved and is still moving both vertically and horizontally. This movement is governed by the internal forces that build the crust and are responsible for variation in its elevation or relief. The internal forces are still active, although not as intense as they were in the past. These variations in elevation are being continuously acted upon by external forces propelled by the energy from the sun. The result is that the Earth's surface is being continuously acted upon by external and internal forces. The internal forces are also known as endogenic forces, and external forces are also known as exogenic forces. The endogenic forces are endlessly raising or elevating the parts of the Earth's surface. With the result, exogenic forces are not able to even out the relief of the Earth's surface. Consequently, the relief in the form of mountains, valleys, plateaus, hills, plains remains, owing to this continuous battle between endogenic and exogenic forces. These physical features such as mountains, valleys, plateaus, hills, plains, characterized by differences in elevation on the Earth's surface, are known as relief features. These form the fundamental physical framework of any watershed and determine the slope, gradients, drainage directions, watershed boundary, and the distribution of runoff pathways. Now, what is a watershed? A watershed, also known as catchment or drainage basin, is a unit of land formed by relief features in which all precipitation drains to a common outlet such as a river, lake, reservoir, or sea. In other words, we can say that it is an area drained by a river and its tributaries. It is bounded by ridges, hills, or other elevated areas known as drainage divides, which separate it from the adjacent watersheds and also determine the direction of surface and subsurface water flow. Within a watershed, all water, whether flowing over the surface or moving underground, eventually converges towards the same discharge point. The size of the watershed can be small or large, like the Indus Basin, Ganges Basin, Amazon Basin, etc. Having understood the concept of watershed, the next step is to understand its main characteristics. A watershed is generally characterized by linear, aerial, and relief features, each of which plays a distinct role in controlling hydrological processes. Linear features describe the drainage network, aerial features define the overall shape and extent of the basin, and relief features represent its topographic variations. Understanding these three groups of characteristics helps in analyzing runoff, infiltration, erosion, water storage, and other processes within the watershed. I will give you a brief description of various features of the watershed. Linear features. Linear features include all the branching network of channels, streams in the watershed, irrespective of their length and width. Channels may be so narrow that one can jump across them, or too wide like Jhelum River, or sometimes more than 1 kilometer wide, such as the Mississippi River. There are different patterns of streams or channels in a particular watershed, which are determined by the rock type and structural features of the watershed, like trellis drainage pattern, radial drainage pattern, dendritic pattern, etc. These features best perform the function of transporting water, sediments, and debris out of the watershed. Now, aerial features. Aerial features of the watershed include the form and surface area of the drainage basin, as well as related features such as interflows within the watershed. Area is a two-dimensional feature, which means it is the product of both length and width, whereas drainage or streams have only one dimension of length, and they are like lines. In general, it may be stated that aerial features of the watershed intercept precipitation, help in recharging groundwater, and supply rock debris, whereas streams move water and debris out of the basin. We now turn to the most important component of the watershed, that is its relief features. Relief refers to the heights of points both on aerial surfaces and line features in relation to the horizontal base of reference. To put it in other way, relief represents both gradient of aerial surfaces and linear features. Relief indicates the rate of drop of runoff and indicates the intensity of transportation and erosion processes. Relief controls speed with which water flows across through the terrain. The key features of relief include elevation, slope, and other quantifiable relief parameters like relief ratio, relative relief, ruggedness number, disposition of contours, and hypsographical curve. Each of these features play an important role in creation of runoff, infiltration, erosion, sediment transport, and even groundwater recharge. To see how relief actually works, we now look at its main features and measurable parameters. Elevation. This is the vertical height of various location points within the watershed in relation to the basin outlet or a datum like sea level. The total basin relief is the difference between the highest and lowest points. In order to understand the general topography and potential energy of the flowing water, the elevation data is essential. For example, we measure a parameter called channel gradient. It is generally described a drop in elevation from the source to the mouth of the master stream in a watershed. It actually is the outcome of the interaction between stream power and lithological features of the watershed. It is a dimensionless measurement and is calculated as RG is equal to ES divided by EM. ES is the elevation at the source and EM is the elevation at the mouth of the trunk stream. If the RG values are higher, they represent greater channel slope with steep V-shaped valleys. The elevation data can be obtained from DM, Google Earth, or through a GPS survey of the watershed. Then slope. It represents the steepness or inclination of a surface. It indicates whether a landscape is flat, gently sloping, or steep. Steeper slopes result in faster surface runoff and increase the chances of soil erosion, while as gentler slopes permit greater water infiltration and reduce the erosion. Slope is commonly measured as a basin slope, which is expressed as SB is equal to m into n divided by a into 100. The m is the total length of all contours within a drainage basin, n represents the contour interval, and a is the basin area. The total contour length reflects the overall relief variation of the watershed, while the contour interval shows the vertical spacing between successive contours. For a given basin, a higher values of m or large contour interval results in a steeper basin slope, while as closely spaced contours make the slope steeper but does not make the total contour length larger. The value of m increases when the basin contains greater number of long contour lines. Then relief ratio. It is a number used to define how steep a drainage basin or watershed is. It compares the total relief, that is the vertical difference between the highest and lowest elevation, and the basin length, that is the horizontal distance between the highest and the lowest point of the basin, particularly parallel to the principal drainage line. It is the total basin relief divided by basin length. For example, if you have a watershed where the highest elevation is 4000 meters, lowest elevation is 1000 meters, and basin length is 20 kilometers, that means 20,000 meters. Then the total relief would be 4000 minus 1000 is equal to 3000 meters. Then relief ratio would be 3000 divided by 20,000, so it comes up to 0.1. So that means a relief ratio of 0.15 suggests the high relief and a steep gradient. Then relative relief. It is a measure of how much elevation varies within a particular area. Instead of taking into account the maximum and minimum heights of the whole landscape, it concentrates on a smaller area or a segment of watershed, like the relief of a valley and the surrounding mountains. It tells us how rugged or flat the terrain surface is. Then ruggedness number. It is a dimensionless morphometric index and is used to describe the degree of ruggedness or dissection of a drainage basin or watershed. It combines relief, that is vertical steepness, and drainage density, that is length of streams per unit area. It is calculated as Rn is equal to drainage density into basin relief, where this dd is expressed in kilometers per kilometer square and h is in kilometer or meters. If the ruggedness number is higher, it means the terrain is steep and highly dissected, which will cause the water flow to be very fast, leading to higher erosion and landslides. Similarly, if the ruggedness number is lower, that means the terrain is gentle or flat, the water moves slowly, and the erosion potential is low. For example, if the basin relief is 1500 meters and the drainage density is 1, so that means 1.5 into 10 is equal to 1.5. This indicates a high degree of ruggedness, which is typical of mountainous areas like the Himalayas or deeply incised plateau regions. Similarly, contour pattern provides a visual expression of slope and relief. For example, if the contour lines are closely spaced, the slope of the landscape is steep, and if wide apart, then the slope is gentle or flat. If the contour lines are V-shaped towards uphill, it means a valley or stream channel, and if the V-shaped contours point downhill, it indicates ridge or super. Where contours are circular, they indicate hill, depression, a dome or a plateau. Then hypsographic curve. It is another measurable relief parameter that explains the evolutionary stage of the watershed. It is represented through a graph that shows the relationship between elevation and the total percentage of land in a watershed that is lying above that elevation. The geomorphic stage of the evolution of the landscape is reflected by the shape of the curve. For example, a concave upward curve suggests a low relief, ancient or mature landscape with gentler slopes favoring more infiltration and enhanced groundwater recharge. Conversely, a convex upward curve usually indicates a young landscape characterized by high relief and steep slopes, indicating increased runoff and more erosion potential. Now that we know the relief features and measurable parameters, let us see how they actually influence runoff and other processes in the watershed. Relief and flooding. Watersheds with steeper slopes, especially those with high relief ratio, result in greater water velocity and the water gets less time to infiltrate into the soil. Conversely, watersheds with moderate to gentle slopes and low relief encourage water infiltration and groundwater recharge. The steep slopes and high relief ratio also increases the potential and gravitational energy of water required for soil erosion and sediment transportation. The increased water velocity erodes more and more sediments, leading to gully erosion, channel formation, slope failure, and the overall evolution of the geomorphic landscape. The watershed with a large area under steep slopes also leads to a decrease in the lag time and results in flooding in the downstream regions. This is a common problem in the upper Jhelum watershed, that is the Kashmir Valley, India, which is bounded by mountainous regions on all sides. The valley is bounded by the Greater Himalayan Range on the southeast and the Pir Panjal Range on the northwest. Among these ranges, Pir Panjal is a tectonically active mountain range with steep slopes, and the apron of the range is gentle, comprising loose, unconsolidated sediments. The rainwater and glacial melt from the steep slopes of the Pir Panjal range, while moving down slope, erode the loose sediments from the mountain valleys, especially the unconsolidated moraine deposits and paleolacustrine and aeolian sediments from the apron of the mountain range. This erosion leads to sediment deposition in the streams that emanate from the mountainous ranges, leading to a decrease in the carrying capacity of the streams. The steep slopes and decrease in the carrying capacity of streams often results in flooding in the low-lying areas. In contrast, low relief watersheds with more plain areas along with good potential for infiltration owing to the presence of permeable rock and soil surfaces allow more water to percolate into ground, thereby recharging aquifers, decreasing the overland flow. Likewise, relief of the watershed has a strong influence on the hydrological response and the shape of the hydrograph. Watersheds with steep slopes develop a short lag time and a sharp rising limb due to rapid overland flow, whereas gentle slopes produce longer lag time and lower peak discharges. High relief terrains also promote Hortonian overland flow, enhances stream power, and increases sediment detachment from slopes, contributing to higher sediment yield and downstream channel aggradation. Furthermore, steep mountainous regions are prone to landslides, debris flow, and flash floods, especially during intense rainfall caused by orographic effects, as can be seen along the Pir Panjal and greater Himalayan ranges. These geomorphic and hydrological interactions collectively amplify flood risk in the low-lying parts of the Kashmir Valley. The impact of relief on flooding is significantly modified by the underlying rock type and vegetation. For example, hard compact rocks of the watershed tend to inhibit infiltration and increase the surface runoff. In contrast, soft or highly porous rocks like limestones and highly fractured, jointed and faulted rocks facilitate greater percolation of water and decrease the velocity of the surface runoff. This phenomena on one hand increases the groundwater recharge and on the other hand results in the growth of vegetation, which ultimately reduces the soil erosion and prevents rockfall. Similarly, dense vegetation intercepts rainfall, decreases the moment of overland flow and provides enough time for subsurface infiltration. In contrast, watersheds with sparse vegetation or no vegetation experience faster surface runoff, thereby increasing erosion and degradation of the watershed. Together, relief, lithology, and vegetation govern the nature and intensity of geomorphological processes operating in the watershed. Relief is an essential driver of water movement and landform development. It strongly influences how streams adjust and erode in the watershed. For example, high relief of the mountainous areas will lead to greater stream power, vertical incision, formation of gorges, deep incised valleys, waterfalls, plunge pools, neck points, etc. The river valley is deep and narrow, headward erosion and sediment production are more prevalent in these settings. Drainage pattern can vary from trellis, dendritic or parallel depending upon the rock type and structure. The basin evolves faster, while as low relief results in the formation of alluvial fans, braid bars, point bars, natural levees and meandering river patterns. Valleys are broad and U-shaped, water velocity decreases, vertical erosion lessens and the lateral erosion is more. These geomorphological processes in turn control the development and spatial variation of soil thickness across different relief zones. Now, relief and soil thickness distribution. Relief plays a key role in the formation of soil by influencing microclimate, drainage conditions, slope steepness, and erosion rates within a watershed. In watersheds with high relief, rapid runoff is promoted by steep gradients, which results in continuous removal of loose weathered material, thereby stopping the formation of thick and mature soils. In these areas, soils are either absent or commonly shallow, poorly developed, and stony to coarse grained in texture. Owing to the sparse or no vegetation cover on steep slopes, unstable slopes, the organic content in these soils is very low. The unavailability of abundant moisture, frequent mass wasting also leads to patchy or sparse vegetation, mostly dominated by water stress tolerant species. Conversely, in low relief areas, slow runoff supports the accumulation of organic matter and weathered material, resulting in the formation of deeper and fertile soils that hold moisture for the growth and development of vegetation. Gentle slopes being stable are also suitable for dense root network, which buttresses the soil, thereby enhancing soil formation. Thus, low relief areas sustain more dense and diverse vegetation, which intercepts runoff, rainfall, increases infiltration, decreases erosion, and supports the long-term watershed stability. Relief also interacts with atmospheric processes influencing precipitation patterns. Relief strongly affects the distribution and concentration of precipitation with elevation through orographic effects. High relief leads to more rainfall on the windward side and less rainfall on the leeward side. It has been observed that mountainous regions with high relief receive high intensity, short duration rainfall, thereby generating flash floods, faster runoff, and debris flow. Conversely, the watersheds with low relief have more even precipitation and show a steady hydrological response. Finally, the combined effects of relief on hydrology and geomorphological processes shape the patterns and intensity of human activities within the watershed. Relief controls land use and land cover patterns by constraining infrastructure, agriculture, settlements, and development in high relief terrain, while making flat and low relief areas suitable for human activities and settlement. Human activities like infrastructure development, such as road construction, result in deforestation and slope alteration in high relief mountainous regions, which disturbs the natural drainage network and enhances soil erosion. Thus, planning of relief-based watersheds is important for sustainable land use management and to mitigate flooding, landsliding, and mass wasting. So this was all about today's lecture. Hope you have enjoyed it well. Thank you for watching.